Hello everyone, welcome to our differential equation class. In this video we introduce a new type of equations called first order systems of differential equations. We are going to start with the main definitions we are going to need. Then we are going to relate these first order systems with equations we already know from previous videos, second order scalar equations. And we are going to study that relation, and this relation is called a first order reduction of the second order system. Then we are back to first order systems, and we are going to study general properties of these equations. So that's the plan for today. Let's start with the main definitions, and this is a 2x2 system of first order linear differential equations. So this is how we summarize that. A system of first order linear differential equations is an equation of this form, where we have a vector variable x function of time, let's say. The derivative of that is equal to a matrix that may depend on time, acting on the variable vector plus some other vector value function. So here in this notation we have that the variable is x of t, the parameter is t is time, for example, and a variable is a vector that has two components. So we have actually two unknown functions here, x1 of t and x2 of t, that they are putting together in this vector value function. Then the coefficients of the system are all together in a matrix that may depend on time and has coefficients a11, a12, 221, and 22. Each one of these coefficients could be a function of time. And then here we add vector value functions where we have two functions. The components are two functions, b1 and b2, function of time. So with these definitions, this here is a 2x2 system of first order equations. These equations, this system is called homogeneous if and only if b is equal 0. So we don't have b over here. This equation has constant coefficients if this matrix, the matrix A here, is a constant matrix. It doesn't depend on time. We don't say anything about the source vector b. This could be different from constant, but the coefficients have to be constant in order the system to have constant coefficients. The system is diagonalizable if matrix A, the coefficient matrix, is diagonalizable. And the other main definition we are going to use all the time is the definition of an initial value problem for a system. So an initial value problem for a system of first order linear equations. So let's first order, I forgot the L here, of linear differential equations, is to find a function x of t, solution of the equation 1, here is equation 1, satisfying an extra condition, which is the functions at the time t equals 0, for example, takes a particular value. Here x0 is a vector with two components, and here x0 component 1, x0 component 2. These are two numbers, so this is a constant vector. For example, you can think 1, 2. So that is an initial value problem, to find from all the solutions of the equation one solution, all the solution that satisfies these extra conditions. And later on we will see that there is only one solution for the system we are going to work with. A few more remarks about these definitions. And of course, this we work on 2x2 systems. Here we introduce the definition for 2x2 system where the vector has two components, the metric is 2x2, and this vector has two components. But this definition can be generalized to n by n systems. So we just need an n by n matrix, an n by n vector, and n variables. But we are going to work in this video and following videos only with 2x2 system. That's why 2x2 is enough for us. In components, how the equation looks like in components. Well, the equation is, recall equation 1 is x prime equal ax vector plus b. And we know what the components, in components, what this equation looks like. This equation looks like, well, the vector x has two functions, x1 and x2, and we are computing the derivative of each component, and that has to be equal to the matrix of coefficients, which we say is a11, a12, a21, a22, acting matrix vector product with the variable vector x1, x2, and the result of that is added the vector b1, b2. Okay, that system looks like in components. If we do all the products, this matrix vector product, and then we have the first component of the equation and the second component, we get two equations which look like x1 prime is going to be equal to a11 x1 plus a12 x2 plus b1, and the other equation is, for the second component, the derivative is a21 x1 plus a22 x2 plus b2. So this is how the system looks. This is in matrix and vector notation. This is the usual notation of the system, and you see why the system is called 2x2. We have two equations in two unknowns, x1 and x2. This type of equations is a generalization of the equation we studied in chapter 1 in a previous video, which is the linear equation for, we call, I think, the variable y prime equal ay plus b. So this is the equation, a linear equation in the variable y, one equation, one unknown. This could be called a 1 times 1 system. And we know how to solve it. Is integrating factor method, for example, or if these are constants, we know how to solve it as a separable equation. But here the situation is more complicated, because although this is very similar to what we have here, then this b is what we have here. In the system, we have the other variable, x2. And as soon as we have x2, we cannot solve it with this equation with the same ideas we had over here, because we have a function we don't know. To find this function, we need to solve this equation. But again, we are going into troubles, because this is what we have highlighted is a equation similar to the equation from chapter 1, but we have something we don't know. And recall, we couldn't solve for x1 because we didn't know x2, and we cannot solve for x2 because we don't know x1. So this system of equation is harder to solve than this scalar equation. We denoted the variable here of the system in vector form as a vector. So, and we are going to write it in several ways in these videos. So the most common way is going to be as a column vector, as we did in our videos on linear algebra and matrix algebra. But there's also this notation as vector as a row using brackets. Both notation means the same. So first component here first, second component here. And this is the horizontal component when we do a picture. This is the vertical component, and these are notation for the vector. But we are also referred to the solution not just as the whole vector, but also as the endpoint of the vector. And sometimes when we want to emphasize that, we are going to use this notation. You see, we have the same functions here, x1 and x2. So from the computational point of view, is this exactly the same thing. But now we are emphasizing the fact that we are representing the solution when we do graphs or pictures as points instead of the whole vector. So when we want to emphasize the point version of the solution, we write it in this way with parentheses. When we want to emphasize that the solution is a vector, we write it like this or like that. So it's just so we are aware that what notation we are going to use in the future. Now, an example of why we are interested in systems of 2 by 2 and n by n linear equations. Well, there are many systems in nature that can be described by this type of equations. For example, the parasite-host system. So here we have two functions, unknown function x1 and x2, which are going to be the population of the parasite, p of t, is going to be our first unknown function, the parasite population, and the other function is going to be h of t, which is going to be the host population. And there are many systems that can describe how this parasite and host interact. Maybe one of the simplest equations is this. The equation for the parasite contains the host, because the more hosts we have, so a parasite could be lice and the host could be mice, for example. The more mice we have, well, this is better for the parasite because they have more food resources. The parasite feeds on the host. So this is an equation that when the population is positive, that increases the rate of change of the parasite. And unfortunately, the more parasite we have, this is bad for the host because it's taking resources from the host. So we have the more parasite affects in a negative way the rate of change of the population of the host. So this is a very simple system. So this is an example of a 2 by 2 system of linear differential equations that describe a real-life situation. Here, in this example, a1 and a2, as we said before, they are positive constants, and this is a 2 by 2 linear system. And if we want to solve it with the equation written just as they are, well, we are going to have a problem, the same problem we described before. As soon as we want to integrate for p, well, we need to know h, but to know h, we need to know p. So there is no way to solve this system one equation at a time. You need to solve it together. And to solve it together, this is what we mean when we say that the system is coupled. You cannot solve one equation and then the other. You need to solve both equations at the same time. By the way, this is an example, is a very particular case of the equation we studied, introduced in the previous page. This is the case of homogeneous, so there is no b term, and it has constant coefficients. These are the coefficients, and they are constants. So just to see this, let's write down this equation in vector notation. So our variable vector is going to contain p and h. So let's introduce here p and h. This is our variable vector. We are going to compute the derivatives, and that has to be equal the right hand sides, which is a vector which has a1 h minus a2 p, and that's all we have. But then this is nothing more than a1 actually 0 times p plus a1 times h, and then minus a2 times p plus 0 times h. So this is a matrix vector product of the matrix of coefficients 0, a1, negative, a2, 0, acting on the variable vector which we define as p, h. So introducing x as ph and the matrix of coefficients as 0, a1 minus a2, 0, well, the system is written in the usual form. Then x prime is equal ax. And this is just one example from nature of a system of differential equations, a 2 by 2 system. Yeah, this is kind of ugly. So let's write it nicely. This is the matrix that describes the system, and we are going to see that the solution of the system, of course, depend on what coefficients we have in the system. There are many more examples that we can think of, and one source of infinity many examples is the fact that any second order linear differential equation, a scalar equation that we studied in previous videos, can be written as 2x2 systems of first order differential equations. So what we are saying here is that any equation of the form y double prime plus a1 y prime plus a0 y equals some function f of t, this is a second order linear differential equation, can be written as a system, a 2x2 system of first order linear equations. And this is what we are going to see now. And also the relation also goes the other way, but we are not going to do much, we're going to make much emphasis on that. But any first order system 2x2, and this here is 2x, let's go to blue again. This is 2x2. Any 2x2 first order system can be written actually as a second order scalar equation, but we are going to focus on this way of the relation. So this is what comes next. A first order reduction is the following. Any second order linear differential equation, so an equation like this, can be written as a 2x2 system of first order equations or something like that. A more precise way to say that is the following. The function y of t is solution of this equation if and only if that function and its derivatives are solutions of this system. So the function y is going to be solution of a second order scalar equation if and only if the function y is the unknown of the system and its derivative here is the other function in the system. So this function and its derivative are solutions of this system of equation where the coefficients you see are related in this way. So let's prove this statement. So proof. The proof is simple. We just have to be very careful what we write. But suppose we let's prove it in this way. It's an if and only if. So in that way, so we need to start assuming that y of t is solution of the second order equation. So y prime plus a1 y prime plus a0 y equal f. Oh, I changed. Now it's not f anymore, it's b. Okay. So now, given in this way of the proof, we know y. So we have y. So once we have y, introduce two functions. The function x1 of t, which is y, and the function x2 of t, which is its derivative. Because of these definitions, we have one equation relating these two variables, which is, if you compute the derivative here, of course you are going to get that. So from here we get that there is a simple the first equation in the system has to be, because of these definitions, has to be that x1 prime is x2. Okay, what is the other equation on the system? Well, the other equation has to be x2 prime. But x2 prime by the definition is y double prime. But y double prime we can get it from here. y double prime is going to be negative a1 y prime negative a0 y plus b. Okay, but we just said that y prime is x2 and y is x1. So this is nothing more than negative a1 x2 negative a0 x1 plus b. Well, here is the second equation of the system, right here. So all this implies, so all the calculation we did here imply that, let's put it here, we have the following system. x1 prime is equal x2 and x2 prime is negative a0 x1 negative a1 x2 plus b. And this is the system that we said is the solution of the second order equation must satisfy. Alright, that's the proof on one direction. In the other direction, well, we start with a system. We start with this system, x1 prime is equal x2 and x2 prime is negative a0 x1 negative a1 x2 plus b. So what do we do now? So now, for example, what we can do is from the first equation we can compute the derivative to this equation. x1 double prime is going to be x2 prime, but we know what x2 prime is, so we put this equation in here. If we do that, what do we get? Well, we get an equation for x1 that is going to be second order equation. x1 double prime is going to be negative a0 x1 minus a1 x2 plus b. But recall that x2 is x1 prime, so we put that again in the system and we get that x1 double prime is negative a0 x1 negative a1 x1 prime plus b. Therefore, x1 must satisfy the following equation. x1 double prime plus a1 x1 prime plus a0 x1 has to be equal b, which is the second order equation we said that is going to satisfy. So that's essentially the proof. We can go one way or the other, from the second order equation to the system and from the system to the first order to the second order equation. Because of the first order reduction that we just mentioned, we can use systems of differential equation to describe the oscillation of a spring. For example, suppose we have a spring attached to the ceiling, a spring like this one with spring constant K that has a mass, an object of mass m attached to the spring and is oscillating in a medium with a friction constant d, and we have an external force acting on the system, on this mass spring system, and we use the usual coordinate system to describe it. Then this we know that the mass spring is going to be described by a second order linear differential equation of this form. This is one equation containing two derivatives of the displacement, the unknown function. But now, because this equation can be written as a system, we can use first order systems to describe the mass spring. And this is how we do it. We start with the equation. This is the equation this is Newton's equation of motion for this system, and we introduce the first order reduction, which is the function x1 is going to be the displacement, the function x2 is going to be the derivative of the displacement, and because of that we have our first equation for the system. X1 prime is equal x2, which is what we did in the previous page. And now what is the equation for x2? Well, x2 prime is going to be, of course, y double prime, but now we have an equation for that, and this is going to be minus d over m y prime minus k over m y plus the force over the mass of the object cosine of omega t. This is the particular force is an oscillating force that we are external force we are adding to the spring. And now we switch this into x2, this function into x1, and we end up with minus d over m x2 minus k over m x1 plus f0 over m cosine of omega t, and that's the system. So this is the second equation, here is the first, and here is the second equation. Okay, so let's write down the equations together. The equations are x1 prime equal x2, and now x2 prime is, let's write x1 first, so negative k over m x1 negative d over m x2, and the fourth term f0 over m cosine of omega t. We are redoing the calculation from the previous page, and now we can write this equation as a system in the usual way. Now they should be the usual way, x1 prime, and here we have x2 prime. This is one vector valued function, has to be equal the matrix of coefficients, that is 0 here, x1 plus x2. This is the first equation. The second equation is negative k over m x1 negative d over m x2 plus, and actually we can write this as a vector, and then the source we can put it in its own source vector, 0 f0 over m cosine of omega t. And because of all that, then we can rearrange now the term in the middle as a matrix vector product. So we have here x1 prime, x2 prime. Here we have a matrix vector product of this matrix, negative k over m, negative d over m constant coefficient matrix, because our second order equation had constant coefficients, x1 and x2, plus the source vector that we had before, f0 over m cosine of omega t. So this is a system that describes the same spring as the second order equation. So let's call this matrix the matrix of coefficients. It's a constant matrix. This is called the source vector for this system, b, which in this case depend on time. And with that we can write down the equation, and well, this of course is going to be, okay, let's use it here. This here is going to be the source vector. So then we have this source vector. The derivative is just that matrix of coefficient x plus the vector b. So first order systems are perfectly fine to describe an oscillating spring. The only thing we need to know is that this system has a matrix associated, which is this coefficient matrix, and the force goes in this vector. And with that, we can use systems to describe an oscillating spring. Let's move on and discuss some general properties of systems of first-order differential equations. Let's start with the linearity property. By that, we mean the following. Given a matrix A, then for all scalars C1 and C2 and all vectors x1 and x2, the following equation holds, and that is the matrix vector product of A with an arbitrary linear combinations of the vectors x1 and x2 is the same as the linear combination of the matrix acting on the individual vectors. The proof of this statement is essentially the definition of the matrix vector product, and that proof is left as an exercise. And now we move on to the next property, which is the superposition property. And sometimes we say that this superposition property is the other side of the coin of the linearity property, because they are deeply related. And the superposition property is the following. If we have two solutions, two vectors, solutions x1 and x2, solution of the homogeneous linear system of differential equations, x1 prime equal ax1 and x2 prime equal ax2, then an arbitrary linear combination of the two solutions is also a solution of the same equation. So the proof of this property, superposition, uses in the critical step the linearity property. That's why we say both properties are deeply related. Let's see why this is the case. So let's go to the proof. Suppose we have x given by this formula, and I'm going to change a little bit the coefficient, the name of the coefficient. Instead of a, I'm going to call them C1 and C2. All right, so suppose we have this function x, which is a function of time, of course, of t, and we compute the time derivative. What we are going to get? Well, it's going to be the time derivative of this expression. These two are constants, so it's going to be the derivative of the individual functions. So we are going to have C1 x, the first function prime. Recall this is a function of time. We don't write it anymore. And then plus C2 x2 prime, which is a function of time. And now, well, but we know what these functions are because each one is a solution of the same equation, so we replace the derivatives by what they are, which is C1a acting on x1 plus C2, the matrix A acting on x2. But now we use the linearity property, this property here. And then, but now we use it in this direction, of course. So we are going to have that this is the same as A acting on C1 x1 plus C2 x2. And that is our definition of x. So this is A acting on x, which now we emphasize is a function of time. And that's it. This is the property we wanted to prove. So the superposition of solutions is a consequence of the linearity of the matrix vector product of the matrix A acting on the vector x. The next property we are going to study is called the general solution theorem. This general solution theorem is very similar to the general solution theorem we have seen in a previous video in section 2.1. And this is the statement. if we have two functions, x1 of t and x2 of t, that they are not proportional to each other, and both are solution of this system of equations, a homogeneous linear system of differential equations where A is a 2 by 2 matrix. If all that happens, then every solution to this equation can be written as a linear combination of the two solutions x1 and x2. The proof of this statement is given in the textbook, and this theorem motivates the following definitions, which are analogous to the definitions given in chapter 2. And the definitions is, first, the functions x1 and x2 that we have here, these are called fundamental solutions of the differential equation if both functions are solution of the equations, like we said here, and the two functions are not proportional to each other. So these two functions that we have in the theorem are fundamental solutions of this equation. The other definition is of a general solution of an equation. The general solution of this equation 2, this should be equation 2 and equation 1 are the same. Okay, so let's put equation 1 is more reasonable because it's right here. So the general solution of equation 1 is given by the linear combination of fundamental solutions, where C1 and C2 are arbitrary constants. Let's see an example of these concepts in here. Show that these two vector valued functions, 2 exponential 2t exponential 2t, and this function here, exponential negative t, 2 exponential negative t, are actually fundamental solutions of this system of equation where here we have the matrix A, and then write the general solution. Okay, so how do we solve this problem? Let's do it here. Solution. Let's start with the first solution that we have in the example, x1. X1 here we put an upper index to not confuse with components of the vector. This function of time is actually a constant vector to 1 multiplied by the exponential 2t. Okay, we want to see that in order to see that the two functions are fundamental solutions, we need to show that both are solutions of the equation. So let's compute from here. We can compute x1 prime. What is that? Well, this is a constant vector, so what is going to happen is 2 is going to drop from the exponential on both components. It's going to be common factor. So we are going to end up with, let's put it here, the vector 2, 1. The derivative is going to act only on the exponential 2t, and that is going to drop a 2, that we can put it on front, for example, 2, 1, exponential 2t. Okay, now we need to do the other side of the equation and see what we get. So we have A acting on x1. What is that equal to? Well, matrix A is 3, negative 2, negative 2, and 2, acting on this constant vector 2, 1, and everything is multiplied by the exponential 2t, so we can keep the exponential outside and do the matrix vector multiplication. So we are going to get 6 minus 2, so we are going to get 4, and then we are going to get 4 minus 2, so we are going to get 2. So we get this vector, and then everything is multiplied by the exponential. And now we can pull common factor a 2, then we have the vector 2, 1 multiplied by the exponential 2t, and here we see that we have obtained the same thing as before. So this proves that x1, this solution x1 prime as a function of time, is always equal the matrix acting on that function at all times. So this is a solution of the differential equation. And exercise, do the calculation which is similar for the other function, x2. This calculation is left as an exercise. So now we know, after we do this part of the calculation, we know that both functions now are solution of the differential equation. In order to be fundamental solutions, we need to show that they are not proportional to each other. So if they are proportional to each other, if there is a constant c such that x1 of t is actually proportional to x2 of t, what that constant could be? For all t, then what if that constant exists, then we have 2, 1 multiplying exponential 2t has to be equal that constant, and then we have the other function has the vector 1, 2 exponential negative t. That is from here. The vector 1, 2, and then the same exponential. So this has to be true for all time. In particular, it could be true, if it's true, it's going to be true at t equals 0. And at t equals 0, that means that 2, 1 has to be proportional to 1, 2, which as vectors we see they are not. They are pointing in different directions, so they cannot be proportional. And we are going to get a contradiction because this implies that 2 has to be equal c, but also 1 has to be equal to c, which from here c has to be equal 1/2. But we cannot have 2 and 1/2, so what happens, what actually is happening is that c does not exist. So if you want it to be proportional, well, the calculation says they are not. Therefore, so x1 of t is not proportional to x2. And then we conclude that then x1 and x2 of t are fundamental solutions. Of the equation x equal a x prime equal ax, where matrix A is of course this matrix here. So what is the general solution then? Well, once we have fundamental solution, the general solution is a combination of fundamental solutions, and that's that. This is going to be a constant c1 times the first solution, which is 2, 1 exponential 2t, plus another constant 1, 2 exponential negative t, and these are all the solutions of the system for arbitrary values of the constant c1 and c2. And this is how we find solutions of a system if we have fundamental solutions. So the whole problem is to find fundamental solutions. In our last example today, we are going back to the mass spring system. In this case, we have a spring that is oscillating without friction, no friction, and without any external forces, and has these initial conditions, some initial displacement and no initial velocity. And we want to describe the movement of the spring using second-order equations, and then we need to describe the same movement using systems of first-order differential equation and see how they look like, the two descriptions of the same system. So in the case of second order equations, we are going to go pretty fast. We know that Newton's equation for this system is given by this equation, mass times acceleration plus the spring constant times the displacement equals 0. There is no friction, so there is no term with y prime, and there is no external forces, so this is 0. We always rewrite this equation dividing by m, and then we have here an important quantity, which is the square root of that is the frequency of oscillations. We are going to see in a minute. So the equation now looks like the acceleration times this omega squared y equals 0. We know how to find solutions of this equation. Recall, we put solutions of the form exponentials rt. Then from here we get an equation for r, which is r squared plus omega 0 squared equals 0. From here we get that the roots are pure imaginary numbers, plus minus omega 0 I. And from here we get the general solution, which is something like this. Combination of sines and cosines, with this number as the frequency of oscillations. Now we have initial conditions. We know that these initial conditions are going to determine the constants C1 and C2, and they actually do, and it's a simple exercise to see that C2 is going to be 0 and C1 is going to be 1 because of these conditions, and this is our solution. And it's not a surprise that the spring is going to oscillate as in this case as a cosine of omega t. That is the actual function, and for the next description, when we go to systems, we are going to need the derivative of this solution, which is the derivative of the cosine, which is negative omega sine of omega t, which looks more or less like this. But this is what the spring is doing, and for example, for this to do this picture, we assume that omega 0 is bigger than 1, but this is just an assumption to make the picture. These are the oscillations in the velocity. These are the oscillations in the displacement for this particular spring. How all this looks like when we do first order reduction and we try to describe this system with vector value functions and a system of first order equations. Well, we write this system in the usual way with x1 of t to be the function, the displacement in this case. Now x2 of t is always the derivative of x1, so in this case is the velocity of the spring. These two definitions give us the first equation, because x1 prime, which is y prime, is actually x2, and x2 prime, which is y double prime, because of the spring equation, is negative omega 0 square y, which is negative omega 0 square x1. So all that can be written together in a nicer way as x1 prime is actually equal x2, and x2 prime is negative omega 0 square x1. So that is the system of equation, that this first order system of equation that describes the mass spring system. And if we introduce a vector variable x of t, which is x1 and x2, these are functions of time, and actually we know what functions are these. These are the displacement and the velocity of the spring. And then we can, with that vector, we can write the system as follows: x1 prime, x2 prime, the derivative of the vector, is going to be equal a matrix which is 0, 1, negative omega 0 square 0, acting on the vector x1, x2. And this matrix of coefficient is very important, is what describes the interaction, the mass spring system. And we have initial conditions. The initial conditions are that x at 0 is what is going to be, well, is y at 0 and y prime at 0. but these are fixed by the initial condition, which is 1 and 0. So this is the system that describes the mass, the first order system that describes the spring, the oscillating spring with this initial condition. And we know what the solutions are. Well, the important quantity here is the matrix of coefficients, which is A1 negative omega 0 square 0. This matrix determines the movement of the spring. And we don't know how to compute solutions of systems yet, but in this particular case we already know the solution and its derivative, so that can be written here and there, and then we can actually write the solution as a system in this way. And now this is solution vector, but recall that we can write the solution as a vector, or as the endpoint of the vector. Both are equivalent ways to represent the same solution. Here, this is how we write the endpoint of the vector. So here it is. Our spring is a point on the plane moving according to this curve or according to this solution vector. You see, these are exactly the same components. So if we do a picture of this solution in this space, it's convenient to use the solution curve, because then the solution is gonna look more or less like this. So what we have here is a plane where we have x1 and x2, which are the components of the solution vector. x1 and x2, these are the axes. And now we plot in that axis this curve, and it turns out to be an ellipse. You see, on the y-axis it oscillates between 1 and negative 1, and on the other axis between omega 0 and negative omega 0. And if you actually are careful and draw this curve, well, this is essentially what we have. That curve. And how we get this direction of rotation? Well, we start at t equals 0. We are at the point 1, 0. 1, 0. So we are here. And then at some particular time, at this time, we are going to have the cosine 0, and the sine is going to be 1, so we are going to be down here. So we are moving from here to there, so this is the direction of rotation. And where are these pictures? Well, these pictures are the function y as function of time, and here time is not in an axis. Is a parameter. It's a parameter of this curve. So if you want to see that function, we need to put we need to see the projection of this of that curve onto the horizontal axis, and then put time here in a new axis, and then you're going to see that this oscillation back and forth are actually oscillations back and forth, like this. And from here you get the actual oscillations of the displacement. And the projection of this curve on the other axis here, well, when you put time, they're going to give you oscillations back and forth, and this is going to be oscillations in the velocity. That's why they have amplitude omega, and we get the other function. So this is more or less, we are going to go in detail in future videos on how we interpret solutions of systems, but here is an example where we have a solution solved in both ways, the old way and the new way. And what type of pictures represent the solutions now in systems? And this type of pictures, which are pictures in the phase space, contains information about the actual solution and the derivative of the solution, which are projections on different axes. So we are going to go in more detail later on in later videos, but this is a good examples to see the two descriptions of the same systems. And well, this is a good place to stop. See you guys in the next video.